All right, let's get right into it. We're going to take a journey today, starting with something you see every day, a simple glass of milk. And we're going to dive deep, right down to the microscopic level to uncover its absolutely incredible secrets. It's a story of chemistry, of structure, and, of course, delicious transformation. So, you ever just stop and think about it? What is it really inside that milk that lets us turn it into a creamy block of butter, a tangy yogurt, or a sharp block of cheddar? How does one simple liquid do all of that? Well, that's the big question we're tackling today. And here's how we're going to do it. First, we'll look at the basic ingredients. Then we'll zoom in on the two superstars, fat and protein. After that, we'll get to the really fun part, how it all transforms. And finally, we'll see why all this science actually matters in your kitchen. Let's go. Okay, first things first. What is actually in your milk? Let's break down the fundamental building blocks of regular cow's milk to see exactly what we're working with. Well, the first thing that jumps out is wow. It's mostly water, right? Almost 88%. But the real magic, the part that gives us cheese and butter and everything else, is hiding in that little 13% of total solids. That's where all the action is. That's where we find the fat and the proteins.
And this chart really puts it into perspective, doesn't it? Look at that giant blue slice for water. It really shows you how much heavy lifting those small slivers of fat and protein have to do. These tiny percentages are literally the foundation for some of our favorite foods. So let's zoom in, starting with the fat.
All right, let's talk about milk fat. And I want you to think of it not just as, fat, but as millions and millions of tiny, perfectly protected spheres of liquid gold. Each one is its own little world. So what you're seeing here is one of those spheres, a milk fat globule. You know how oil and water don't mix? Well, milk is what's called an emulsion, which is just a fancy way of saying it found a clever workaround. It packages all the fat into these microscopic droplets, then wraps each one in a special membrane that lets it float happily in the watery part of the milk. So let's peek inside that globule. The vast majority of the fat in there, like over 90%, is made of these molecules called triglycerides. And the structure is actually pretty beautiful and simple. You've got one glycerol molecule in the middle, kind of like a backbone, and then 3 fatty acids attached to it. That's it. That's the fundamental building block.
But, and this is a huge but, not all fatty acids are the same. This is so important. Up top, you see a saturated fat. Notice how it's a perfectly straight chain? That means they can pack together really tightly, like a neat stack of bricks. But look at the bottom one, an unsaturated fat. See that double bond? It creates a permanent kink, a bend in the chain. Because of that kink, they can't pack together neatly. That bend is going to be super important later, so remember.
Okay, we've got the fat down. Now, let's move on to the other hero of our story, protein. And specifically, we're going to focus on one type in particular, the protein powerhouse known as casein. This stuff is, no exaggeration, the secret to cheese.
And this chart shows you why it's so important. It's not even close. A whopping 80% of all the protein in milk is casein. That other 20% is whey. Because casein is the overwhelming majority, its behavior is what really dictates how milk transforms into things like cheese.
Now, casein proteins are what we call hydrophobic, which is a sciencey way of saying they are water-fearing. They do not like to be floating around in water by themselves, so they do something really smart. They huddle together for protection. They form these big, complex clusters called casein micelles, held together by these tiny little bridges of calcium phosphate. So you might be wondering, if they all hate water, why don't they just clump into one giant, useless ball? Ah, this is the genius part. On the outside of each micelle, there's a special protein called capsaicin. It has these little chains that stick out, kind of like a hairy layer. These hairs have a negative charge, so they push away from each other, like magnets repelling. It's this fuzzy force field that keeps all the micelles perfectly suspended. It's just brilliant. So, we have our tiny fat globules floating around, and our stable casein micelles all keeping their distance. Now for the fun part. The magic trick. We're going to see how we can intentionally break that stability and turn liquid milk into a solid curd. Okay, our first method involves a concept that sounds complicated but is actually pretty simple, the isoelectric point. All it means is that for every protein, there's a specific pH level where its electrical charge becomes 0. It's not positive, it's not negative, it's neutral. And for casein, that magic number is a pH of 4.6. When it hits that point, the repulsion force field goes down. And here's what that looks like. Normal milk is up around a pH of 6.6, where all those little micelle hairs are negatively charged and pushing each other away. But when you add an acid, like when bacteria make lactic acid to create yogurt, you lower the pH. As you get closer and closer to 4.66, you cancel out that negative charge. The repulsion vanishes and the micelles start to cling together, forming that soft, delicate curd we know as yogurt.
The second method is way more dramatic. Instead of messing with the charge, we just go in with what are essentially molecular scissors. An enzyme like rennet, which is used in cheesemaking, specifically targets those protective hairy bits of cabecasin and just snips them right off. And boom, the force field is gone. The now exposed micelles are sticky and they immediately grab onto each other, forming that firm, rubbery curd that becomes the foundation for almost all cheese.
Okay, I know, that was a pretty deep dive into biochemistry, but what's the payoff? Why does any of this actually matter? Well, let's connect all this science back to the food that's literally sitting in your fridge.
Hey, remember that kink in the fatty acid chain I told you to remember? Well, here's where it pays off. This graph shows something called the iodine value, which is basically a scientific measure of how soft or liquid a fat is. And look at that. It spikes big time during the summer months.
So what's happening? It's simple. In the summer, cows eat fresh grass, which leads to more of those kinky, unsaturated fats in their milk. More kinks mean the fat molecules can't pack together tightly. And what does that give you? Softer fat. This is it. This is the scientific reason that summer butter is softer and more spreadable than the harder, more brittle butter you get in the winter. It's all about the kink.
And here's another real-world example. If you've ever heard that you shouldn't use super cold milk to make cheese, well, now you know exactly why. When you chill milk way down, the delicate structure of that casein micelle actually starts to fall apart a little. Some of the protein and calcium literally leak out. This makes the whole structure weaker, which means it'll take longer to form a curd, the curd will be weaker, and you'll end up with less cheese. It all comes back to protecting that micelle.
So the next time you spread butter on your toast or slice into a piece of cheese, I hope you see it a little differently. Is it just food, or is it the delicious, edible result of a perfectly balanced emulsion, a self-assembling protein structure, and an absolutely brilliant piece of molecular architecture, all hidden inside one simple glass of milk?